Good day and welcome to another edition of Let's Learn Math. We're going to be working with polynomials, and specifically I would like to talk to you about understanding what division means and understanding how division relates to polynomial division and the different ways we have to describe all of that. So recall some vocabulary. This number here is the divisor because it's going into the dividend and it's going to produce a quotient, just so we can have a common language here. But back in grade school they might have taught you some long division. It's a really tedious algorithm, but understanding it helps us understand polynomial division a little bit better. The first idea is you're supposed to, I'm sorry, I've got a couple synonyms for division. We write them this way when we're going to use the long division algorithm. We write them this way in grade school, elementary school. But once we get up to the algebra level and beyond, this is how we show division. And some people would say that's a fraction, and I would say, yes, what do you think division is anyway? That's why the symbol looks like it does. It's a symbol for a fraction. So fractions mean divide, divide means fraction, and this is just a way to organize the division algorithm. So the other thing that we're trying to do is we have to understand we're trying to take the number 6,025 and to break it into 32 equal parts. If we had $6,725 and we wanted to share it with every member of my Algebra 2 class, which is too big, we could figure out how much money each of those individuals would get. Anyway, to review the algorithm, we're supposed to be looking at numbers that are how many times does 32 go into 67? Now, it's really erroneous because we're not actually looking at how many times 32 goes into 67. We're actually asking how many times does 32 go into 6,700. And we have to go under the number 67 because we need this number down here to be below 6,700 so that we can continue dividing. Anyway, we multiply the 2 times the 34, bring down the 64, and then we subtract to find out what's left to be divided. So really it looks like a 3, but it's actually 325. So now we know there's going to be $200-something for each member of the class. We also know that there's still $325 left to be divided. So we have 200 plus going to be some more. So we bring down the 2 so that we can just talk about the hundreds in the simplest possible way, and it turns out that 32 goes into 32 one time, but that's really 10, and we multiply 1 by 32, and we subtract, bring down the 5, rinse, wash, repeat. And that gives us leftover $5 that I, the teacher, will keep for my pain and suffering. Anyway, we will say that that $5 has yet to be divided amongst the 32, but it's going to be some change at the end of the day. So the notion here, though, is, number one, that each of the numbers in the quotient is going to end up being above its corresponding place value, so that the place values are being held by the position of the number. So the 2's, if that's 200, goes above the hundreds place, etc. The other thing to remember here is we start by dividing into the largest portion of the number and work our way back. But when we do that, we multiply, subtract, multiply again, subtract, and so forth. We're going to apply the exact same algorithm to our polynomials. Before we do, though, I want to go back to how we express division in algebra. We express division in algebra using fractions, and realize that what we did by completing the long division algorithm is we turned this fraction from an improper into a mixed numbered fraction. Now we can understand the value of the fraction better because it's 210 with some change. But if you take this equality, which is a true statement, and make everything, both sides, 32 times bigger, we can produce a new statement that is 6,725 is the product of 32 210s plus 5 more. So these are all sort of truths that are expressing the same reality, basically. How does that work for polynomials? Well, in polynomials, we're going to use our x power, or each term, as a place value. So instead of the thousandths place, the cube place. Instead of the hundredths place, the squared place, and so on. But the algorithm itself, really straightforward. Make sure when you set up your division, that your dividend has every place value accounted for it, and we'll look at an example of that later. But here again, we're going to figure out how many times does 3x go into 6x cubed. Essentially, all you have to do is take 6x cubed and divide by 3x, and you get 2x squared, which you'll put over the squared place value. Multiplying 2x squared by 3x gives us our desired value, and the leftovers 2x squared by negative 2 gives us negative 4x. And make sure you're keeping everything straight. I use a different color to show the subtraction, so I make sure I subtract it. The reason it's confusing, of course, is this is negative 4x squared, but we have to subtract the negative 4x squared, which results in adding. So we end up with just a squared value, and just as before, we're going to bring down the linear value and find out how many times does 3x go into 3x squared, and the answer is just once. When you multiply 3x minus 2 by x, you get 3x squared minus 2x. Don't forget, I like to change the color to remind myself that I did do what I was supposed to. I subtract, which turns out to give me adding a 2x. And we have negative 3x, bring down the 4, and multiply by negative 1, so we can match the negative 3x. Now it'll be plus 2, which again we subtract, and now we have leftovers. The 2 still has to be divided by the 3x minus 2, and we just say, I'll do that later. And just as before, you can see the division algorithm is expressed here as a fraction. We lay it out in long division format so that we can handle the algorithm itself. But now, instead of focusing on the process, let's focus on the truth that we have revealed. We have a quotient and a remainder, so this fraction can be expressed as a quadratic function plus some extra stuff. Another way to look at it, of course, is that if we had the function g of x was just the numerator of f of x, that numerator can be expressed as the product of the quotient times the divisor plus the remainder. Again, that's based off of the same mathematics that I uncovered over here. This is another way to look at the numerator expressed as the product of two numbers plus a remainder. Same truth applies to polynomials. Here's another truth that's revealed later. I just want to show this as a reminder for those of you who already know this truth, that when I got a remainder of 2 by dividing by 3x minus 2, that it's also true that f of 2/3 is equal to 2. If you wanted to know, you can put 2/3 into x right here. This would become 0, zeroes everything out, and just leaves us with the 2. So there's a connection between division and evaluation of numerator functions. But we'll jump off that bridge later. This video is getting kind of long already. So I'm going to show very quickly another example of an algorithm, or of the same long division algorithm, but I'll just jump to it. If you want to see how I did each step, feel free to pause the video. But this is only here to show you that we have to account for place values with zeros, just as we do here. If you were dividing 10,003 by 204, you would not just make it 13 divided by 24. That'd be ridiculous. So the same thing holds. We need to have our place values in place, both for the numerator and the divisor, or in the denominator, which is the divisor. The 0x has to be accounted for, otherwise you're going to have crossed place values here. It's not going to work. That's pretty much going to conclude today's video, or this portion of the series. Next video is going to talk about a shortcut that works for some special cases of division called synthetic division. Stay tuned. I know it's exciting, right?